Hi, everybody. I know you haven't heard from me in a little bit. Sorry for the late posting. We are going to be spending today talking about something called buffers. And when we're talking about buffers, we have to be able to understand why there is such a thing as a buffer and also what is a buffer defined as. A buffer has something called a common ion in it, or sometimes it's referred to as the common ion effect. And so that usually involves an addition of an ion already present in a system. So the ion that is part of, for instance, the weak acid. Okay, so for instance, if we were talking about the common ion in the solution HC2H3O2, we would be specifically talking about, and I'm going to get my marker here, we would be specifically talking about the C2H3O2 as our common ion. So you see that as the conjugate base, basically. A common ion would be another compound that has that same anion. So you would see something like sodium acetate as being another compound with a common ion. Now, when we make a buffer solution, it has to, its job is to resist changes in pH when small amounts of strong acids or strong bases are added. That is the definition I want you to make sure you have for this. And what makes up a buffered solution is it's made of a weak acid and its conjugate base, or a weak base and its conjugate acid. Okay, so what does that mean? Let's take a look at the NH3, so ammonia and ammonium buffer system, so we can see that ourselves. And I'm going to scroll this down here. Okay, so taking a look at ammonium and ammonia, ammonia is the weak base, and the ammonium is the conjugate acid of that. And so these equations here are referring to, well, what if we have a strong acid added to the ammonia? You'll notice that that immediately makes, look at that, our conjugate acid. So it makes more conjugate acid. What if we add an addition of a strong base? Well, then what happens is you simply make some water and some more weak base. So this buffer system made up of both of these two parts are going to act together to keep a large change in pH from occurring. Let's take a look at another example. What if we have, let's see here, what if we have a, there we go. What if we have the system of the acetic acid and the acetate ion? That is our system. That is the weak acid and its conjugate base. Same thing happens again. If we add a strong acid to this weak acid, we end up simply making more weak acid. If we add the strong base to the weak acid, we go through an acid-base reaction and make just water and more conjugate base. Okay, so you obviously will need to know immediately how to do calculations of this sort. So bear with me here. I'm going to start you out doing calculations of this sort with somewhat of a longer method here. And then we are going to move on to, okay, so what about, is there a shortcut way to do it? And of course there's a shortcut way to do it. So this problem says a buffered solution contains 0.50 molar acetic acid, the Ka is given, and 0.50 molar sodium acetate. So to calculate the pH of this solution, obviously we put it into a rice table and we use the Ka expression, and we remember to negate our pluses and minuses x, and so we end up with a pH of 4.74 after we calculate our hydrogen ion concentration. Okay, we've done that before. That is not a big surprise. That is review. Now, what about, now I want you to remember, keep that number in mind. What we had when we started off with this solution was 4.74 for its concentration. Sorry, for its pH. What about if we add a strong acid or a strong base into it? So let's take a look at what if we add a strong base like NaOH into this um, weak acid conjugate base buffer system. So the first thing we have to do in red is we have to complete the stoichiometry. So first thing we recognize, okay, the sodium hydroxide is the limiting reactant. Those moles are used up and only 0.01 moles of the weak acid are used up. The weak acid and the strong base will make some conjugate base and some water. And we're not going to worry about the water. You know, water is not included in the Ka expression. All right, so the strong base is all used up, and we have now made a buffer, a continued buffer solution. And now we need to know, well, what is the pH of this remaining buffer solution? Because we've used up, by the chemical reaction, all of the all of the weak base. Sorry, I said the wrong thing. All of the strong base. Okay, so with that in mind, we can reestablish our equilibrium calculating using Ka, so we can find the hydrogen ion concentration, which then we take the negative log of, and we find that the pH went up only a tiny bit, not a lot, and this is exactly the way our buffer should act. Remember, its job is to limit the amount of change in pH. So that's cool and all, but that does seem like a lot of work. What if we had a way that we could completely eliminate the Rice table and the Ka expression portion of this? Well, I propose to you something called the Henderson-Hasselbalch equation. It is written as pH is equal to pKa plus the log of the concentration of the base, meaning the conjugate base, over the concentration of the weak acid. All right, so some things are, remember, we have to have a conjugate acid base pair. We want our buffer solution to be optimal, meaning that they should have the same concentration, but it's okay if they do not. And we can't have too dilute of a solution. All right, so those are not big deals for us to follow. Those are going to be mostly of what the types of problems we're going to see. Okay, so we are going to at least get started with Rice to begin, because I want to be able to make the point that, in fact, we still have to do our stoichiometry. Don't we always have to do our stoichiometry? But we also can get to the point where we might not need the Rice table. So first things first, we are going to do our stoichiometry, and I'm actually going to turn my stoichiometry all red over here. Let's see here. Changing it from blue to red so you can see the stoichiometry portion of things. We have our initial number of moles. I take it back. We do not need stoichiometry for this part, simply because on this part we are not adding any base in. So we can simply calculate our pH of this system doing it the old-fashioned way, which is what you see here, with the pH coming out to 4.62, or doing it Henderson-Hasselbalch with the pH also coming out to 4.62. Guess which way I like better. Just guess. Just guess. Of course, it's the Henderson-Hasselbalch way. And again, what we have here is we have the pKa, and you might be wondering, well, where did that come from? So that's where we take the Ka, here is our Ka, and we put it into the negative log format, and we get the pKa. So we are actually using the Ka to calculate the pKa. That goes into our equation, plus the log of the concentration of the conjugate base over the concentration of the weak acid. You have to do that math first before you take the log of it. And so then you end up with 4.62, which is exactly the same pH. So Henderson-Hasselbalch equation works really well, and that's the one we're going to try to use throughout. If you forget and you start to use a Rice table, please, it's okay. Use a Rice table. All right, so what if we have that same buffer system that we just had from up here, that buffer system right there, but we are going to add some strong acid to it. So there's our strong acid that we are going to add to it. All right, so here comes our strong acid. First thing we have to do is we have to do our stoichiometry here. And so the stoichiometry, I have moles of strong acid, I have moles of conjugate base, and I have moles of weak acid. So it is the strong acid and the conjugate base that are going to react first, which is what you see here. Those are going to react. All the strong acid is going to be used up. It's the limiting reactant. And I just noticed a typo here. We're going to make sure that we have the correct number of moles. Oh, that's right. Okay. So now we have then what is formed afterwards is actually our buffer system. Of course, we have to recreate the molarity, which we're going to take the moles of each one that remain after and divide by the total number of liters. And for those of you going, now where did the total number of liters come from? Let's make sure that you remember that we had 0.1 liter from the HCl and we had 0.455 liters of the weak acid. So keep in mind that that's what you had there. Okay, so getting all that together, we get our molarities of each one. Now we could go through and do the whole regular equilibrium like in the earlier chapter, getting a pH of 4.42, or we can just do this last part. Remember, stoichiometry first, then Henderson-Hasselbalch. You remember, you are going to have both both concentrations to be able to do the work that is required. So that is what we have. Some other things. Keep in mind that if you are doing the Rice table, you do have to remember to negate your X's. All right? But if you do Henderson-Hasselbalch, you don't have to remember to negate your X's. Very exciting there. All right. So your job by Friday is to finish exercise 4, exercise 5, exercise 6, and exercise 7. After Friday, you have to finish what comes next. We will talk about acid-base indicators later, but beyond the acid-base indicators is, and let me scroll to it, is some IB practice. For Monday's turn-in, you will be completing the IB practice that is provided here on the rest of this. So ultimately, you will be turning in 2 things. If you wait to turn it all in until Monday, then you're just turning in one, you're doing 1 submission. Otherwise, you're going to do 2 submissions, 1 for Friday and 1 for Monday. All right, everybody. Hope you're having a good day, and I will talk to you soon. Please remember that if you are going to need some help, we can schedule some Zoom time if you need some tutorial time. I expect tutorial time with this one. If you need it, please let me know. Bye-bye.